In today's lesson, we're going to be talking about measures of variability. So in the last lesson, we saw how we can compute different ways of speaking about the location of a distribution or a data set. And in today's lecture, we're going to be looking at how spread out or how variable is that data set and how we can measure that. So for the lesson today, we want to be able to understand and interpret the range, variance, and percentiles of a data set. And alongside variance, we'll also be looking at the standard deviation, but as we'll see, those two are quite connected. And we also want to understand and interpret box plots, which is going to be another visualization that sort of corresponds nicely to measures of variability. So what are we really trying to do when we're thinking about variability? And the question that I would ask is, what does location miss, right? So you can see that I sort of have three different distributions overlaid on top of one another. And you could think about these as sort of being the limiting box plot or the limiting histograms for these distributions. And we can tell that the three of them are quite different, right? We can see that they're clearly quite, if you were drawing from any of these distributions, if that's the data set you got, you're looking at very different data sets. But the locations are going to be the same, right? You can see that the mean and the median are both going to be around 0 for all three of these distributions. And so the idea is that there's obviously a lot more going on with a distribution than just the location that we might be measuring. And variability is a major component of that. When we're thinking about variability, we're thinking about how spread out the data are. So some data are more spread out than others, and we say that that means they have higher variability. In other words, with higher variability, we have less concentration around our measures of location. Okay. Now, just like there were many different ways of measuring location, we have several different ways of measuring our variability as well. And the simplest measure of variability is simply the range. And the range is given by our maximum value less our minimum value. So it's just what is the total scope of values that we have observed and sort of how much space does that occupy. And it's a very crude measure, but it's oftentimes useful and it's quite intuitive to understand. We also might think about the sample variance. And with sample variance, what we're thinking about is squared deviations from the sample mean, right? And so what we saw was that our sample mean is a measure of central tendency. Let me zoom in a little bit on this here, right? So with our sample mean, we were thinking about it as one way of measuring the location of the distribution, right? And so you can think about taking sort of a measure of xi minus the sample mean to say how far is that point from the sample mean. Now, generally, when we want to measure a distance, we don't want you to be able to cancel out positive and negative distances. And so instead of just looking at this directly, we square it, right? And we force all of them to be the same. So whether something's 2 above or 2 below the mean, we don't really care. That just becomes 4. Right? And then if you just take the sample average of this, so you go 1 over n times by the sum over all of the data points for this, that gives us the sample variance, right? So it's the average squared deviation in our data set. We denote this with s squared, and the thing that I'll point out right here is that oftentimes you're going to see a slightly different formula for this. We can ignore that for now. We'll come back to that at a later point in the course. And so for now, we could just think about this as being the sample of the sample average of squared deviations. And we also talked about the standard deviation. The standard deviation is just the square root of the variance. So we have our range, maximum minus minimum. The variance is the average of squared deviations, and the standard deviation is the square root of our variance. Now, we can look at some properties of our variance and our standard deviation. The first is that they both have to be greater than or equal to 0, right? And that's because we're summing up a bunch of squared numbers, and so the smallest that they could be is 0. And the only way that they're going to equal 0 is if every single data point is constant. Okay. Now, the standard deviation is going to make most sense to discuss when we're thinking about the mean. And the reason that we sort of square root the variance and think about the standard deviation is because we can bring it back to the same scale, right? So if you're thinking about measuring distances or say measures in centimeters, when we're thinking about the variance, we're taking centimeters and we're squaring them, right? So it's this unit, it's this mismatch of units here. So when we square root, we're back into dealing with centimeters again. And so the standard deviation and the mean are quite nicely used together, and we'll do that a lot throughout the course. We'll often use a shorthand here where we define this SXX to just be the sum of squared deviations, right? And so then we can take the variance to be SXX divided by n and the standard deviation to be the square root of that. And that's just a notational point. We can also use a shorthand here where if you wanted to calculate this by hand, which we're not going to be doing a lot of during the course, but it's useful to know, if you can sum up the squares and then take off n times the average squared, that's going to actually simplify down to that. And so that's a useful exercise to be able to show that that is the case. Now, one important point to note is that adding constants never changes the variance. Okay, and so the idea, and we could actually show this algebraically if we wanted to, but if you were to take xi as our data, right? So we have some data set from I equals 1 to n, and we consider adding some constant to this. So we take xi plus c from I equals 1 to n. The variability in each of these two data sets is going to be exactly the same, right? And that makes a little bit of sense. If you're just shifting the distribution around, you're not changing how spread out it is, right? Now, of course, adding constants changes our measures of location, but it's not going to change the variance. And as a result, it's also not going to change the standard deviation. If we multiply by constants instead, that's going to end up multiplying our variance by a value of c squared. And again, if you're thinking about why that's the case, if you're looking at our formula for our variance there, because we're squaring everything, you're going to factor out that c. When you're factoring it out, it's going to become c squared, right? And so we're going to multiply the variance by a square. As a result, the standard deviation is just going to be multiplied by c, but it's actually going to be multiplied by the magnitude of c. Again, whether c is positive or negative, we know that the standard deviation is always going to be positive. Okay. The reason that these two properties here are most useful is because we sometimes will want to do unit conversions. So if you have Fahrenheit, you convert to Celsius, right? That's going to involve multiplying by a constant here. And so we can calculate a variance for Fahrenheit and use that to translate it to a variance in Celsius or vice versa. So when we're talking about what does the location miss, the answer is variation. And on this graphic here, I've now included what the standard deviations are. And so the really tall middle distribution there has a standard deviation of 1. The green one in the middle has a standard deviation of 2. And the blue one, sort of the most spread out, has a standard deviation of 3. So you can see sort of the skinnier, the less spread out, the lower the standard deviation. The wider, the more spread out, the larger the standard deviation. Now, the other point that we can sort of start to make here is going to be related to our median, right? So we said that the standard deviation and sort of by extension the variance is related to the mean. So what's going to be related to the median? And the first thing that we have to do is actually generalize what we were thinking about with the median. So a median is a value that divides our data so that half of it lies above and half of it lies below, right? And we can ignore the even and odd cases. For right now, it's so that 50% sits on either side of the median. Now, what if instead of using 50%, we swap that to be p% and 100 minus p%, right? So say 20% below, 80% above, or 75% below, 25% above. When we do this, we're finding what are called the pth percentile, right? So the 25th percentile is the value such that 25% of the data is below it, 75% of the data is above it, okay? In this sense, we can consider the median to be the 50th percentile. And the percentiles we normally care about are going to be the 25th, which we call Q1, or quartile 1, the 50th percentile, which gets the name of the median, as well as the 75th percentile, which we'll call Q3. Okay. And so again, these are just going to be values that divide sort of a portion of our data above and below. The Q here is for quartile because we're splitting up our data into fourths. And you can sort of think about the quartiles as being the median for the upper half and the lower half, right? So Q1 is if you just take the lower half of your data and you find the median there, that's going to be what your quartile 1 is. And if you find the median of the upper half, that's going to be Q3. Okay. Now, another way that we can measure the variability of the data is what we would call the interquartile range, or the IQR. And we calculate IQR by doing Q3 minus Q1. Right? So this is going to also be a measure of spread. When we're thinking about the standard deviation being related to the mean, we think about the IQR as being related to the median. Right? So if you're going to report the median, you probably want to report the IQR with it. If you're going to report the mean, you probably want to report the standard deviation with it. The IQR can be useful for detecting outliers, and there's generally this rule of thumb, which is that if you're 1.5 times your IQR away from your nearest quartile, so if you're 1.5 times the IQR above Q3 or below Q2 or Q1, then you'd think of them as being mild outliers. And if you're 3 times away, then they're extreme outliers. But again, I'll point you to the previous discussion we've had around outliers, which is to say outliers are useful to detect, but we probably don't want to remove them from our data. Now, sometimes what we'll do is we'll list the minimum, Q1, our median, Q3, and the maximum for the data. And these 5 numbers are referred to as the 5-number summary. And they sort of give you a good sense of how is the data distributed, what's the spread, and what is the location, right? So we refer to that as the 5-number summary. We can also display the 5-number summary graphically using what we would call a box plot. So here we're looking at the penguin data once again, and what we have are 3 different box plots. So down at the lower end of the lines that's sticking out are going to be our minimum and our maximum. And then within the sort of box itself, you're going to have your Q1, your median, and your Q3. Now, in actual fact, the lines that are drawn out are not typically drawn as the min and the max of the data. And instead, it goes 1.5 times Q1, or 1.5 times the interquartile range instead, right? And so then what you can see in this first red box plot here on the left is there's 1 dot drawn above it. And what that would say is that there's 1 outlier that's beyond that 1.5 times threshold, right? But generally, you can think about the box plot as simply representing the 5-number summary, where the lower part is the minimum in the data, and that might be a dot, that might be the end of the line. Once the box actually starts, you have your 3 quartiles, and then the maximum is drawn at the top. And so what we can see is that, for instance, the Gen 2 penguins are sort of below the other 2, right? There's not a whole lot of overlap in that distribution, and that's really easy to see visually within these box plots, whereas the Adelie and Chinstrap are quite similar. To try to summarize what we just talked about with all of that, when we just report location, we're missing the nuance of a particular distribution. And so we also want to consider the spread or the variability of the data. We can use the range, the standard deviation, and the variance as all common methods for measuring variability. We can also generalize our median to be sort of any value we want, arbitrary values. And from this, we can get the interquartile range. With our interquartile range, we can form our 5-number summary, which is a great way of just summarizing the data very quickly. And if you graphically display our 5-number summaries, then what we're doing is looking at box plots. So between the location and the variability, that gives us a really good way of indicating sort of the distribution of a data sort of numerically. And so I'd encourage you to sort of think about all of this a little bit more, and I will see all of you in the next lesson.